Okay, welcome everyone to my session writing a full-text search engine in TypeScript. Before we start, I want to dedicate a huge round of applause for the NDC crew and the organization. This conference is amazing. Thank you all. So, I know that we just had lunch, so the possibility of me boring you that much to go to sleep right now, it's really high. So I put a couple of memes here and now, to start making things a bit more fun and spicy possible, during the talk. So before we start, I'd like to introduce myself. I am Michele. I'm from Milan, in Italy. I work as a senior software architect at Nearform. I'm a Google developer expert and a Microsoft MVP. And I built a full-text search engine, yet another one. So you might be wondering why, and we will get there, I promise. But before we get there, I'd like to thank my company, Nearform, for letting me being there today. We are a professional services company. We are specialized in Node.js, TypeScript, DevOps on Azure, Google Cloud, AWS, whatever, and we are hiring remotely. So if you're interested in working with people that maintains the 8% of all NPM modules out there, which are responsible for 1 billion monthly downloads, please let me know after this talk. But we started with a question: why? Why do I want to write yet another full-text search engine when we have such beautiful solutions, right? We have ElasticSearch, we have Solr, we have Algolia. They are beautiful products. And I would lie if I didn't say that ElasticSearch, specifically, has been the open source project that made me fall in love with open source. And nowadays, I'm working full-time open source, also thanks to ElasticSearch. Then, I'd like to say that what I cannot create, I do not understand, and I'm quoting Richard Feynman in that. And I wanted to learn more. As I said, ElasticSearch has been incredibly influential in my career, so I wanted to learn more about how it works, and how can I build my own little toy, And by the end of this talk, I will show you what I built, and we can discuss it. So I also want to state now, so you are in time to go to another room if you want. This talk is going to be a journey through algorithms and data structures. And I know that now you feel like, oh my God, I'm trapped in a very boring talk about data structures and algorithms, but don't worry. I promise this is not going to be that situation where you have to learn a lot of useless stuff just to pass an interview. I want this to be actual useful information for you and can potentially help you in your daily job. So with that being said, I also want to convince you, being a TypeScript developer myself, that there is no slow programming language out there. There's just bad data structure and algorithm design from now on, DSA. So when it comes to measuring performances in programming languages, we know that Java and C# are faster than JavaScript and PHP. Ruby is really slow. Python is quite slow. Well, I believe that if you know data structures and algorithms, things can change, and I have some benchmarks at the end of this talk. So we can eventually start talking about full-text search. Before getting there, we need to ask ourselves, what the hell is full-text search, right? So full-text search, and I'm quoting sybase.com, is a more advanced way to search a database. Full-text search quickly finds all instances of a term, a word, in a table without having to scan rows and without having to know which column a term is stored in. Full-text search works by using text indexes, and a text index stores positional information for all terms found in a columns you can create text index on. So if you feel a bit confused, I promise you, by the end of this talk, you're going to understand perfectly what is written here. So before we start implementing it, let's see a couple of popular alternatives. We already mentioned Elasticsearch and Solr, for example, which both relies on Apache Lucene, which is the full-text search engine itself. We also have Algolia, which is the only closed source product in this list, and it's another amazing production-ready product, just for you to know. We also have a new generation of search engines. We have Meilisearch and Sonic, both built in Rust, with, of course, performances in mind. And I'd encourage you to take a look in those, because these are great products, actually. When it comes to JavaScript, as you may guess, how many JavaScript developers do we have here, first of all? That's amazing. That's awesome. OK, so you perfectly know that there are tons and tons of packages. I selected the 3 that I use the most. So Minisearch, which is perfect. I love it. Fuse.js, and Lunar, which sadly is not longer maintained. Just for you to know, if you need JavaScript embeddable full-text search engine, you also have these options. So where do we want to start to learn more about full-text search? First of all, let's try to understand which is the kind of data that we want to store and retrieve. So let's start with the simplest data possible. Let's say we have the following documents, simple array of documents. These are quotes from movies. So we have like It's Alive from Frankenstein. We have a bunch of other documents and quotes. And we need to understand how we want to store this data and what we want to run as a process on this data too. So first thing first, we want to tokenize our data, and we will take in consideration the quote right now, the quote property, because it's a sentence and makes more sense, possibly. So when we go tokenize a sentence, for example, It's alive, you will notice that we are removing the single quote. So it's, for example, becomes an individual word. And you do the same in the second quote with you have, you've, becomes you've altogether, because we are tokenizing. So we want to remove, based on particular rules that we're going to see in a bunch of seconds, we want to remove stuff that we don't really care about. For example, double quotes, single quotes, question marks, etc. And we do that, again, by using rules that can depend on the language of the data we are putting into our search engine. For example, we have like Dutch, which has a specific set of rules we have to respect. In that case, it's a regular expression that helps us splitting a sentence depending on the data, on the language we have. We have Greek, we have Nepali, Hebraic, and so on. We also want to remove all the accent and the diacritics. So for example, naive, as you can see, has a diacritics on the letter I. We just remove it. We do the same with facade and jalapeno. Because at the end of the day, first of all, people is not good at searching. I am the first one. So if I have to search for jalapeno, I'm Italian. I don't have this on my keyboard. It's really, I have it, but it's really hard for me to reach it. So I just type jalapeno with an N, So by removing this, I'm giving more support for typo tolerance, for example. And also, Spanish users can just type jalapeno the correct way and find the right result straight away. So removing diacritics, it's pretty easy, actually. We have a map of regular expressions, and every time we encounter like an A, we look if there's a diacritics and just remove it and replace it with capital A, lowercase a, etc. That's really, really easy, but that's a process we want to do on all of our charters we're going to insert in the database. So after that, we lowercase all the tokens. And of course, if we do lowercase the tokens, that means we can't perform case-sensitive search. So keep that in mind. Most search engines are lowercasing all the tokens by default, but you can opt in for maintaining uppercase characters too, of course. Then we want to remove the duplicates. Why is that? We want to remove duplicates because we just don't want to duplicate data. One problem you have when you're building a full-text search engine is that the index size, and we're going to see what an index is going to grow exponentially. It's going to become very, very huge. So we want to remove duplicates to ensure that the index size will stay compact. We can store, though, a token, like a number 2, for saying it's alive appears twice in that sentence. And we can use that number when we use a classification method such as TF-IDF, I don't know, which helps us building more coherent search. But we will discuss about that later on. Then we want to remove the stop words. So there is a lot of process going on, right? We want to remove the stop word, but what is a stop word in first place? So stop words are a set of commonly used words in a language. Examples of stop words in English are a, the, is, are, etc. Stop words are commonly used in text mining and natural language processing to eliminate words that are so commonly used that they carry very little useful information. So let's see if that's the case for us. We have like alive. It's alive. Now just alive. Because it's, as an individual token, does not carry any meaning, Also, the same for like got to, do, I in the second sentence, and was, of, what, gonna in the third and last sentence. Of course, stop words depend on the language. If you have to remove Italian stop words or Norwegian stop words, they're going to be different. So you want to have like a dictionary of stop words that you want to remove from your indexes. Then we are getting to my favorite part, personally, of every tokenization process, which is the stemming process. So stemming refers to the process of removing parts of words. For example, we have lucky, which becomes luck. So we maintain the meaning, but we contract the word to its stem. So we have like chocolates, which is plural, and becomes chocolate, singular, which is it's not a problem because the meaning is the same. So when a user searches for chocolate or chocolates, we can just say, OK, you search for something containing chocolate, so here you are. Of course, we can keep both tokens if you want to perform like exact search. So that's a possibility, of course. But by default, we just stem everything. And of course, this depends on the language. Again, if you're developing a full-text search engine which only supports English, you can just have a stemmer. But like, if you want to support all the language in this world, you have to build a very different stemmer because the rules for stemming a word can depend on the language itself. And this is why I want to introduce Snowball. So Snowball is a personal project of Martin Porter. We will see later who is this guy. And Snowball, it's written in C, can be compiled in JavaScript, can be imported in Rust, can be used in Ruby, C#, Java, whatever. And it's meant for creating stemming rules and basically compiling down a stemming algorithm in C to be imported in other languages. So an example of Snowball, which is, again, open source, so everyone can use it, is this one. So this is an English stemmer. We can see, oh, no, it's the other way around. OK, we can see like consign, which gets stemmed to consign. Again, remains the same. But then we have consigned, which gets stemmed to consign. And that's because these words has the same meaning. So we are storing the meaning of a word, not the entire word itself. And again, I can store both the meaning and the stemmed word if I want to perform exact match. But this is what you're going to get by default on pretty all search engines. And so a couple of examples. Again, I'm Italian, so I could develop like a stemmer for an Italian search engine, but it's easier if I use just the Snowball algorithm, right? And again, I know nothing about German, so I want to use Snowball, or we will see later the stemming algorithm used by Snowball itself. And given that we are in Oslo, I want to keep that for a couple of seconds so you can see in Norwegian how it behaves. So maybe it can be a bit more helpful than Italian and German. OK. So by the way, this is Martin Porter, and he is the author of the algorithm that we're going to see in a couple of seconds. So one nice thing about the Snowball project is that it has some HTML pages that basically tells you, like, this is the algorithm you have to follow, for example, for English, which is different from the algorithm, the stemming algorithm you're going to use in French, in Italian, in Norwegian, etc. And this is a screenshot taken directly from the Snowball website. So if you don't want to compile like a C program into JavaScript, in our case right now, you can just follow these instructions and build the stemmer directly into your program in your favorite language, be it C#, F#, Haskell, I don't care. These are the steps you're going to take to succeed. And of course, we were saying it depends on the language. So from time to time, you don't really know what is the input language for a given text. So you might want to use something like Node language detect, which is, of course, a library that uses an algorithm to determine the language of a given sentence. We are not going to deep dive into that because I only have 60 minutes. But this is really interesting, and I really encourage you to go see what it's all about. So this is the final result, right? We have from it's alive to just alive, and a bunch of other tokens. But now we should ask ourselves, how do we want to store those tokens? We have just normalized our data, right? So how do we store it and get ready for a monster? Because algorithms and data structures are identified in this talk as monsters. We have to start thinking about data structures. But don't worry, It's going to be super easy, I promise. So let's start from the easiest data structure possible. And let me introduce it that way. Let's say we have an array of 6 elements, and we know for sure that there is a document containing the word chocolate. We want to find it. Of course, we have a linear way to do that. We enter the document number 1, we look up all the documents, all the sentences, and we say, is there the token chocolate, for example? No, it's not there, so let's go next one. It's not there, it's not there, it's not there, it's not there. And eventually, we are in the worst case scenario, so the last one. It was in the last document. And that's a problem, because the time complexity required for doing that, it's O(n), which means if we have 1 billion documents, we have to scan through 1 billion documents to find that specific word in our worst case scenario. And we might want something more performant. We might want to perform this operation in O(1), so cost some time, meaning if I have 1 billion elements, I perfectly know where to find the correct one in one shot. So as a computer science scientist myself, I want to introduce an overused data structure, which is called Hashmap. And yes, this is literally me. So let's see what hashmaps are all about. Hashmaps are used to store data in key value pairs. So this is an example of data of my favorite stuff. So animal, dog. You know, I have a dog. It's called Linux. I love him. That's another story. And book, algorithms to live by, highly recommended. My favorite city is Florence, and food, chocolate. So let's say we want to find chocolate. We can do that in O(1) if we have a very good algorithm, and we will get there, by using hash maps. So for creating a hash map, and like in JavaScript, we typically use maps. In PHP, we use associative arrays. In Rust and Java, we just use the hash map classes, I guess, and that's really it. But if you want to start something from scratch, we just create an array of, let's say, 6 elements for now, where every single element is undefined by default. Then we use an hashing algorithm. We have a key and a value. Let's say we hash the key, in our case, food. The hashing algorithm will return a number which is greater than or equal to 0, and is less than or equal to the total length of the array. Like, it will tell us where to position our value inside of this array. So food, for example, with our hashing algorithm, will put chocolate in position number 5, so in the 6th position for our element. The same for language. The hashing algorithm for language will return 3, so we store it in the 4th position of the array, starting from 0, of course. And the same for book, color, animal, city, and oops. You might be wondering, OK, the hashing algorithm must be very, very tough to write at this point, right? Actually, it's not. It's pretty easy. You can condense it in just a few characters. It's not super optimized, and this is not guaranteeing you that you will get results in O(1) constant time. But you can test it, like if you create an array of 10 elements and we hash food, it will return 2. If we hash book, we return 7. And hello Oslo, we return 9. So when asking for a key, we know the exact position of its value inside of an array. So that means that with a good hashing algorithm, the time complexity is O(1). And I want to highlight this. You need a good hashing algorithm to be in O(1) situation here. Bad hashing algorithms are causing collisions, which means that multiple keys gives the same number as a result. So you have to create an hash map instead of an hash map, or put everything inside an array and then loop over the array. So it's not really worth it, but that's another story. Again, let's keep things easy. So that means that when we say, OK, but where is city? We have the array. We have the hashing algorithm. Where is city? It would say, OK, position number 2, so 3rd position inside the array. And what is food? Food, chocolate, is in number 5, so 5th index of the array in that case. But that's not enough to find chocolate inside of our array of elements in O(1). We need, get ready for the other monster, we need an inverted index. In fact, this is a regular hash map. So let's say we have our documents, and like alive is in ID. The ID for the document alive is ID number 1. ID for you ask yourself, etc. is ID number 2. So document ID, you know. And this, when the keys are, how to say, when the elements inside of the arrays, in that case, are in the right succession that you find them in the original phrase, this is called a forward index. We don't need that. We need an inverted index, which means instead of saying, OK, the key is the ID of our document, we say, OK, the key right now will be the token itself, and the value will be an array containing reference to all the documents containing this word. So the token alive is contained in document with the ID of 1. The word you is contained in documents with ID 2 and 3, so 2 distinct documents. And chocolate, you can find it only in document where the ID is 3. So this is how we get the full document in constant time. But there's still a problem. We want to optimize for space, and we will see why. And we might want to create prefix-based search. So let's take this example. We have intersect, interstellar, intergalactic, international, intervene, internal. So these are all tokens with the same prefix that points to documents. And first of all, we are wasting a lot of space. If you think of like indexes containing like 1 billion tokens, how many prefix repetitions do we have? That's a real problem. And if I have like a type ahead functionality in my full text search engine, let's say I just type inter, for example, I want to have all the following results, right? Because I don't have an exact match. The inverted index allows us to have an exact match. So if I search for intersect, that's perfect. But if I search for inter, there's nothing. So trees to the rescue, yet another monster. And get ready, because trees are an amazing source of memes. So it's really important to learn trees in order to get these memes. Please do that. And in that case, I'm, of course, talking about the prefix tree. So let's see what's all about. So let's say we have the following tokens, so private, primarch, prime, and primate. It is clear that they share a common prefix, right? So a prefix tree, let's start with something simple, like a linked list, right? It's really similar at the beginning. So when we have just one word, we have a root node, which I don't know if you can notice, but it's in a poor choice of colors. I'm super sorry. But it's in orange. Then it's linked. There is a pointer to another node containing P that is linked with a pointer to R, then I, then M, and finally E. E is in green, and when there's green, it means this is the end. Oops, this is the end of a word or a token, as we want to call it. So let's say we have prime, and we want to insert primarch. As you can see, we basically create a common prefix, which is PRIM, and we branch. So IM, at this point, won't have just one pointer to one single node, but to 2 different nodes, which then proceeds in 2 different roads. So prime and primarch on the left. We want to insert primate. That's perfect. We branch at the A level. So we now branch here. Primarch goes there, and primate the other way around. We want to insert private. We branch a little bit higher at this point, so PRI, private on the right, and all the other branches on the left. But if we want to insert something totally different with no connection to other prefixes like art, we just branch at the root level. And if we want to insert, for example, artist, which not only has a common prefix with art, but includes the whole word, we just say, OK, so this is green, as you can see. So art, T, is the end of a token, but also has a pointer to I. So it means that this is a word on its own, but then continues down to artist. And then we can use a prefix tree as an inverted index to store reference of a token with the document. Let me show you how. So let's say we have the following words, and we say that like primarch is included in documents 1 and 3. Primate is included in documents 2 and 4, for example. That's cool. We just store these references at the end of every individual word. So that when we say art, OK, art is contained in document 457. artist in document 4 and 7, and so on. So we just migrated from an inverted index to prefix tree. And of course, this is not as efficient as an inverted index. In fact, the time complexity for this algorithm is typically W times L, where W is the number of words and L is the average length of that word. So it's not as efficient, but it's still pretty efficient, and we will see some benchmarks later on. And of course, when you're building a full-text search engine, you can create multiple indexes. So you don't have to choose if I want an inverted index or a prefix tree or a direct acyclic graph, for example. We can have everything, maybe depending on the user prompt. So if the developer wants to have multiple choice, like this search engine only allows prefix search, good, you only keep the prefix tree. It allows exact search, exact match, and prefix search. Awesome, we will put an inverted index here and prefix tree here. So no problem, you can create multiple indexes, and you can use multiple different data structures, such as inverted indexes, forward indexes, prefix trees, direct acyclic graph, B-tree, and tree map. So you have high choice, but okay, I will keep the following slide while I'm drinking a bit. Thank you, Linus. So talk is cheap, show me the code. Yeah, let's see some code. But before we get there, I just want you to know that I tried to implement a full-text search engine with two mainstream paradigms, like object-oriented programming and functional programming. I'm a former Haskell programmer, so I just wanted to try. But I had some problems with both paradigms. So before we get there, I just love to highlight a couple of problems that you might encounter in your JavaScript development career. So let's say we want a search engine with the following features. It has to work on every single JavaScript runtime. It must be as small and compact as possible. It must be as fast as possible, because that's the point of having a full-text search engine, you know. And it must be easy to serialize data. So that means like I can save data in memory, on the disk, whatever. So just for giving you an example about the first point, these are some of the popular JavaScript runtimes. We have like edge computing on Cloudflare workers and Netlify functions, or Lambda at edge for AWS. We have Node.js, Dino, and Ban, which are not very compatible, except for Dino, which is maintaining compatibility with Node. We have React Native. We have browsers. So as you can see, the JavaScript ecosystem, when I say that JavaScript is a universal language, that's why. It runs literally everywhere. But if you write a search engine which is specific to browsers, you might want to use browsers API, right? Which are not available on Node. And you cannot write server-side code inside of your JavaScript bundle, which means like if I have a call to the file system just to retrieve some data, store some data on the file system, it's going to crash on the browsers. And the same is for servers. So I don't have browsers and runtime-specific dependencies on servers. Like dino.filesave, I think it's like that. It's not working on browsers. It's not working on Ban. It's not working on Node. It's not working anywhere. It's working only on Dino. And the same for Node.js file system, of course. And when it comes to edge functions, if you think of Cloudflare workers, for example, it has a limit of 1 megabyte for your script. So it must be small, really small, tree shakeable if possible, so that if you deploy something, you don't have like an in-memory structure that gets updated, but you only want to perform search on a pre-made data structures. We will see later what that means. And of course, with React Native, for example, you don't have browser runtime specific dependencies. And all of these give me some big trouble when it comes to object-oriented programming, for example. First of all, with object-oriented programming, the problem I had with that specific situation, I want to be clear, with that specific situation, is that the state was, of course, hidden, and it was very, very complex for me to create plugin system to allow runtime-specific features. And it was not tree shakeable. I know with JavaScript we have prototypal inheritance, we can work around this, but it's getting more and more complex. So if I have like a class with an insert method, for example, I have to bring that insert method or delete method or whatever on the edge, even if I don't want it, for example, which is not good. I also had problems with the FP approach. So mainly performance is a memory footprint. And that's because when compared to imperative approach, FP in JavaScript tends to be a bit slower. So I know on paper, functional programming should be faster. We all know that practically that's not very true. And about memory footprint, functional programming is advocating for immutable data structures, which has a larger memory footprint. So I'd like you to know that whenever you work in JavaScript, imperative programming, most of the times, will be the fastest alternative you have, always, no matter what. There are some very talented engineers that can work around that, but this is the norm for people like me that is not so talented, you know. So imperative programming in JavaScript is winning when it comes to performances, at least for me. So yeah, let's see some code. I don't expect you to read every single line. Let me just make you feel what it's written here. Let's say a node in our prefix tree has an ID, which is a unique identifier for that node, a key, which is typically the individual character in our word. For example, if we have the word node, N is a key, O is another key, D and E are two separate keys for separate nodes. Then we have the entire word stored as a reference, a pointer to the parent node, pointer to parent children, and an array of documents. So these documents are the document IDs, basically. So this is where the inverted index comes in. And is a Boolean, which says, this is the end of a token, yes or no. That's really it. And when we go implement it, when we have the create function, as you can see, we are not really creating an entire block immediately. We just mutate the block after. So we create an empty block and then add data. So this is where the imperative approach really helps in JavaScript. With objects and arrays, you can always modify them without having to copy them. So you always have a reference to the object. You can just modify it. And when it comes to prefix trees, you have to know that in JavaScript, when it comes to modifying an object shape, that's a very expensive operation. But with a prefix tree, we have 26 letters in the alphabet, so we have a maximum number of 26 nodes down a single token. So we know that we won't go that far, so we are not modifying a shape that much. We can then, for example, update parent. Just as an example, you can see we take a node as a parameter and a parent node, so we can update it, and we just mutate them. We don't copy anything. We just go mutate stuff, which as a former functional programming, I'm pretty scared to say, but this works very, very fast. When we have our tree, eventually we have to insert stuff, and we basically traverse the tree. If we can't find a node, we create we have I don't know, artist. We have art. If after the T we can't find the letter I, we just create it and traverse the tree again. And when we go find all the currencies, you will notice, I'm not explaining this algorithm, it's a simple traversal algorithm, but you will notice that at a certain point, we will see tolerance. What the hell is tolerance? Why is that? So as an Italian speaker, when it comes to writing in English, I write a lot of bad things. I'm very bad at writing English, you know? So for example, I want to find word, but I misspell it. But still, I want to be able to get all the currencies of the word inside of our index. Are you getting scared enough? Because the solution requires dynamic programming. And I wanted to put that slide because I thought that dynamic programming was rocket science. It is not, actually. Dynamic programming, by its definition, is an algorithmic technique for solving an optimization problem by breaking it down into simpler subproblems and utilizing the fact that the optimal solution to the overall problem depends on the optimal solution of its subproblems. I understood nothing. Gonna be super honest. So I'm gonna explain you that using the Lewiston distance algorithm. And here, Kermit, it's going crazy. But don't worry, I can't say it's easy, but I can say that I can try explain it. So the Lewiston algorithm calculates the last number of edits operations that are necessary to modify one string to obtain another string. It is used in spell checker, correction systems, and search engines. If you use Elasticsearch, for example, they are using Levi-Stein algorithm. And also, I guess, Algolia, it's closed source, so I don't know for sure, but I guess. So if we pass like moon and lions as parameters to a Levi-Stein function, we want to get 3 as a result. Why is that? Let me show you. First of all, we need to know that we have 3 allowed operations: insertion, deletion, and replacement. So we want to transform moon into lions, okay? So we look at the first letter M. We have to replace M with L. Then we go in next letter, O. We have to replace O with I. O and N can remain the same, but we need to insert a new letter, which is S. So starting from moon, we have lions in 3 steps. This example has been taken from a YouTube video that I'm going to quote at the end of the talk, because it is brilliant, and I'm going to give you the reference if you want to rewatch this from someone that is better than me at explaining this, I want to be honest. So we just use our intuition, but how do we actually compute that, right? So we have to introduce the dynamic programming table, where each cell in that table is a sub-problem. And again, the optimal solution is the total solution of the sub-problem, etc. I can't even remember. But let's make it simple. We have capital lambda, which means empty string for starting, then lions on the x-axis, and moon. So let's make an example. If I have to if I have to transform MO to L, what is the edit distance? Someone wants to guess? From MO to L? Who said? 2? You're correct. So it's 2. We just replace, what was that? OK, we just replace M with L. Then we remove O. So 2 operations. That's correct. Let's try another one. MOO to O. Super hard to tell, but what is the edit distance in that case? It's 2 again. That's correct. That was a trick. But as you can see, we basically start like here, MOO to this letter here. So from an empty string to an empty string, it's the same, so nothing. From an empty string to L, we insert. So insertion has a cost of 1. Every single operation has a cost. The cost is 1 in that case, because we insert just one thing. From empty string to Li, 2 insertions, so the cost is 2. Then 3, then 4, then 5. Pretty easy. When we go from top to bottom, the situation is a bit different. We start from M, and we want to get an empty string, so we remove. So the remove operations has a cost of 1, so we remove 1. 1 is the cost. MO, cost is 2. MOO, cost is 3. And of course, moon to empty string, cost is 4. Then we get in that situation. How do we do that? Well, I'm about to say thankfully, but I'm not thankful for the formula, because it's messy. I don't have a degree. I have no idea. No, okay. I studied a bit for this talk, but it basically says that the minimum edit distance is defined as the minimum of 3 operations: delete, insertion, and replacement. Minimum is a keyword here. So let's try. We said that we could go from up to bottom. So we have to remove 1. So remove has a cost of 1, plus the fact that we have 1 here. So the total cost is 2. OK? That's what this formula says, hopefully. If we move from left to right, we have to insert. So insertion has a cost of 1. We have 1 on the left. So the total cost is 2 again. Then we have replacement. So replacement in our formula is defined as a distance between 2 charters. If the charters M and L, so M in that case is 1, L is 1. If they are the same, which is our case, the cost is 0. Otherwise, we have to subtract one to another. In that case, it's 0. Replace operation has a cost of 1. So we said that the minimum distance is the less costly one. In that case, is the replacement. So we do replace. In that situation, this is a bit different because the difference between I, which is 2, let me show you again. So I, in that case, is 2. M is 1. So we have to subtract 1 to 2 from 2, so 1. The replacement costs 1 plus the difference, so 2 in total cost. And as you can see, we have the deletion, which costs 3, because we start from 2 and we add 1. The insertion costs 2, and the replacement costs 2 again. In that case, we choose whatever. I will keep both just for the sake of, but we can choose because they are the same. We continue again until we get in that situation. And don't worry, I'll make it easy. We basically steal this part of the formula, which very, very shallowly says, OK, just bring it from the upper left corner. So we basically take this. And when we complete our table, we end up with that value in the bottom right corner, which is 3. And yes, this is the edit distance between lions and moon. So we replace M with L here, which is the first cost. Then we replace O with, what is that? With I. Then second O and N can remain, and then we insert the S. So as you can see, what we saw in this slide, we actually have implemented using the programming dynamic programming table. We can actually do that with every single word: horse and poser, edit distance of 3, raise and raise, which is very typical for non-English speaker like me. You know, raise, it's rise. I don't know. Or rise. You know, they are really similar to me, so I might misspell them while I'm typing. And again, the Levy-Stein algorithm, it's quite complex, if you ask me, to be explained. But it's really easy to implement, actually. So as you can see, it's just a bunch of, and this is a pretty optimized one, OK? Just a bunch of charters. I'm not explaining that. But I will leave the slides if you're interested, and I'll be around later on to explain that. So one nice thing is that we can perform the edit distance on both strings and trees. I'm not going to go through this, but I'm quoting again the YouTube video where I took inspiration from for this specific explanation. This YouTube video is called Tree Edit Distance and Levy-Stein Distance, and it's brilliant. If you're interested in porting that reasoning from strings to trees, this is a beautiful video to start with. And if you're more into reading like I am, there is a beautiful paper called Simple Fast Algorithm for the Edit Distance Between Trees, Replay, and Related Problems from Zhang and Sasha. And again, simple, fast. No, it's not simple. Don't even try. We are going through the end of the talk, and we have a tokenizer, a prefix tree. We have typo tolerance. We also have an inverted index. We can finally create a full-text search engine, and that's what I did. So I want to present Lira. So Lira, it's actually an open source project that you can use today, which is full-text search engine capable of running literally everywhere. So let me show you how it works. You basically, it's tree shakeable, as I said, so you can create a new instance just by importing stuff. You create a schema, and when you create like author field or quote field, this is where you're gonna insert, like author is a prefix tree or an inverted index, quote is another inverted index or another prefix tree. You then insert or use the insert batch operation to not to block the event loop, of course, and just insert stuff. Of course, this must be following the schema. Then you just search. So you like search for if with a wildcard when it comes to searching properties, so that you can also specify an array of properties like search just in quote, search just in author, or in both, you choose. And we have an elapsed time, so a total count of element and elapsed time. Can you guess? Is this seconds, microseconds? What is that? Milliseconds? This is microseconds. You might say, OK, but you have just 4 documents. It's clear that it's microseconds. Yes, but I made some benchmarks. So I took 1 million movies from the International Movie Database, injected everything description, cast, titles, whatever. And I started searching for believe, for example. And I retrieved a lot of documents, like should be 1,200 documents. I'm sorry I didn't put that. By the way, in 41 microseconds. If you search just into the title index, 39 microseconds. So we are in the millionth or a second area here. And I didn't do anything special. I just followed the algorithms and the data structures. Criminal minds, which is composed of two different words. Of course, you have to perform search on criminal. You have to perform search on minds. You have to look if they appear one after another in the original array. So, in the original document. So here, where you want to use forward indexes, for example. And in 1 million of entries, you can do that in 187 microseconds. Again, micro, millionth of seconds. And Lira right now supports 23 languages. And you can, again, it's tree shakeable. So a stemming algorithm, it's really heavy because it's not an easy algorithm. So you can import just the stemmer that it's important to you, in that case, the Italian one. Or you can create your own stemmer. So if you want to play around with stemming algorithm, just download Lira and write your own stemming algorithm. In that case, it just append ish to every single token ish, you know? You can also import custom stop words very easily. You can concatenate with the existing one depending on the language, which by default is English, of course, or you can delete them, do whatever you want. And again, at the beginning of this talk, we had some goals. We wanted our project to work on every single JavaScript runtime, to be as small as possible, as fast as possible, and easy to serialize data. We did that, and we also added a powerful plugin system. So if you use, for example, the Lira Search plugin, data persistent plugin, which is runtime specific, because assessing the file system, for example, is different in Node, in Dino, in Bun, or other runtime, in Graal, VM, if there's anyone using this, you know. But you create your instance, you feed the data, and eventually you just persist the data on disk. You can choose your format. By default is message pack, which is also a format used by Redis, or you can use dpack, JSON. You can implement protocol buffers. That just works. Afterwards, you can just import that data. So you use the restore from file or restore from memory if you want to run that on a browser. And you're good to start searching again. Or you can deploy a distributed scalable search engine. You create a new Lira instance, feed the data, export the indexes persisting them on S3, and just call a Lambda function. You call a Lambda function, you download the data, you perform search, and that's it. And of course, you don't terminate the function, so the data remains in memory. And that's really it. You can use the same APIs on React Native or a browser, for example, allowing offline search. So you create a Lira instance, feed the data, export the index in memory on your browser, and use the in-memory index on React Native or browsers. Or you deploy, for the very first time ever, a full-text search engine on an edge network using Nebula. So Lira, it's named after the Lira constellation because of its distributed nature, and nebulas are, you know, where stars are born, I guess. So this is why we named that Nebula. And I have a little demo. Let me show you. Oh, yeah, I'm not doing that live. I want to be honest. But yeah, so we basically have a Pokédex. We just install Nebula. OK, we have it. So you see, we have two documents, data.json, which is an array of Pokemon, and Lira.yaml, which is a configuration file for Lira. Let's see. If we cut Lira.yaml, we'll see a schema definition, sharding, for example, automatic sharding. So we automatically split the index size, because again, on Cloudflare, for example, you have a limit. You can only have 1 megabyte of data in memory. So we take care of that. We deploy multiple workers. The data type, so in that case, JSON, but you can also use a JavaScript file exporting an asynchronous function to call a database, to collect info from a user, whatever. You can literally use whatever you want. And then a target. In that case, only Cloudflare is supported. We will support Netlify and AWS Lambda at Edge later on. And the worker name, which is Pokédex, again, and if we want to run tests on the data before deploying it. So let's cut some data. So this is the data format. As you can see, it follows the schema definition. And just run, hopefully, Nebula deploy, so Nebula D. And in 5 seconds, you deployed it to Cloudflare workers, and you just use your URL to query the database. In 5 seconds, you deployed the first full-text search engine capable of running at the edge. So forget about cluster management, because edge networks are automatically managed by service provider. Deployment, data consistency, we take care of that with Lira. It's super easy for us. And of course, it's free and open source, so I'm not selling anything. That's just a project. Please open issues. Please contribute if you want. If you're interested in learning more about how search engines work, I am here. And I will be also on GitHub if you want to follow. So that was all for me. Thank you so much for following. I leave my contacts. I mostly live on Twitter, so if you want to reach out, I'll be glad to answer any of your questions. I guess we have like 5 minutes for questions. I'd be glad to answer if there's any. Thank you again. OK.
How would you deal, for instance, in languages like Norwegian or German, that words are composable? So a word with a meaning is a composition of 2 words.
Yeah.
How do you deal with that?
OK, I will repeat that so I know that I understood and everyone can hear. So you mean during the stemming phase, how we deal with, for example, in German, when words are composed, right? Yes, that's a good question. I had a similar question for a couple of Italian words, and the stemming algorithm takes care of that. When I say that Martin Porter did an awesome job with a snowball, I mean that he literally found a way to deal with that kind of possible inconsistencies. So if you follow the step-by-step algorithm in German, which is very, very complex for that reason specifically, you shouldn't have any problem. Anyway, you can always extend your own stemming algorithm to deal with very specific words. So if you care about a dictionary of words, you can say, OK, when I see that word, I will treat it differently. So it is common from time to time to use dictionaries so that you say, OK, I see this word, I will treat this differently, etc. And also when it comes, sorry, you give me an assist. When it comes to edit distance, for example, you also want to use dictionaries so that, for example, if you have, I don't know, word, but there's no document containing the word, the token word, you have an English dictionary, and you say, OK, maybe you're looking for that. So dictionaries are an important part of any search engine. I forgot to mention, so thank you for your question. I can't see anything. It's incredible. OK, I guess that's all. Thank you again. So enjoy the rest of the conference.